So this is a very interesting chapter and something that will help you score quite well on your exams too. Number systems for me is also one of the chapters that I generally push students on because, as I said, it's not only easy for you to score on, but it'll also help you understand a lot of things in detail. So first, I'll talk to you about what the family of numbers is going to look like, and if you just like to draw a little flow chart, you can actually categorize into two parts. The first part is just called real numbers, and the second part is called imaginary numbers. Let us try and understand what each one is. When you talk about a real number, these are numbers that you can definitely put or represent on a number line, and all of us know what a number line is. And while imaginary numbers are those that you cannot represent on a number line. So I'm just going to strike that off just to let you know what works where. Now, under real numbers, you have various categories that we could talk about. The first one is called as rational numbers, and the second one is called as irrational numbers. Now, let us try and understand what each one is in detail. When you talk about what rational numbers are mostly those that you would be able to work with almost on a daily basis. And let's try and understand what some of this could look like. So I'll just put up the heading for you. That is going to be rational numbers. And under rational numbers, we'll sit and figure out all the possible numbers that come under this category. First, let us look at what the form is going to be. Every rational number is always of the form p by q, and q should never be equal to 0. And the other condition that you should always keep in mind is p and q must be integers. You cannot have them in any other form except integers. Now that we have understood this a little more in detail, let's take an example of this. Let's take an example of 4 by 5. If you notice, 4 and 5 are both integers, and the other condition is 5 is not equal to 0. Since both these conditions are met, I call this number as a rational number. There you go. So we say 4 and 5 are integers and all of that. But there's another thing that I also want you to understand. The HCF for 4 and 5 is 1, which means they are co-prime with respect to one another, which means 4 and 5 are in its simplified form. Let's take another example. Another example is that of 5, which can just be represented as 5 by 1. Let's go back to the definition. We notice that both 5 and 1 belong to integers. We also know that 1 does not equal to 0 or is not equal to 0. The other thing that we also notice is 5 by 1 is already in its simplified form, right? And as I circle 5 and 1, I'm just trying to tell you that these are numbers that are going to determine whether they're rational numbers or irrational numbers. Now let us classify rational numbers into further categories. The first one is called integers. The second one is called natural numbers. We can have another category that calls out whole numbers to come under rational series. Fractions, as we've just worked with, 4 by 5 and 5 by 1 are all rational numbers for us to understand. Now that we've understood this, let us try and do a bit of operations on rational numbers. We all know that rational numbers are of the form p by q. Q should not be equal to 0, and p and q must belong to integers. Now let us look at part A of what rational numbers is going to look like. Part A of rational numbers is where we are trying to represent rational numbers on a number line, and this is what I'm just going to put up now. So let's first talk about inserting rational numbers between any two given rational numbers, and you can expect questions around this for about maybe about 2 to 3 marks in your exam, and you should be in a position to do this well. So the first part we're going to talk about is inserting rational numbers between two rational numbers. Now let us take this with a simple example. We know this is a number line, and we're going to mark 0 on the number line. Any rational numbers can definitely be represented on the number line. Now let us take maybe one small example. Let us take 2 by 7, and let us take another number 5 by 7, and let us find out how many rational numbers we could really insert between them. In general, you would be able to represent infinite rational numbers between any two given rational numbers, but let us find out an easy way of doing it. Now I have 2 by 7, I have 5 by 7. I know 3 is between them, 4 is between them. So 3 by 7 and 4 by 7 automatically become two rational numbers between 2 by 7 and 5 by 7. Let's try another example. Let us find 10 rational numbers and let us find this out between 1 and half. Now the first thing that you need to keep in mind is you write the two numbers first, which is 1 and 1 by 1. So 1, I can always have a denominator as another 1. What I'm also going to do next is I'm going to multiply the fractions by suitable numbers such that the denominators become same. So if you notice, on my first fraction I have 2 as a denominator, on the second one I have 1 as a denominator. So I've multiplied them such that my denominators now become 20. So my left fraction becomes 10 by 20, right fraction becomes 20 by 20. Now let me insert the numbers in between. 11 by 20, 12 by 20, 13 by 20, and I can go on. I can go on and get all the way to 19 by 20. And you know what? You can also insert further between 19 by 20 and 20 by 20 and make it as 19.1 by 20. Again, I am showing you an example here. Between 13 by 20 and 14 by 20, I can have 13.1 by 20, 13.2 by 20, 13.3 by 20, and so on. But there is one thing that I want you to keep in mind. Whenever you are following a method such as this, always keep it in its standard form, which means you need to pull out the decimals and then you will have to introduce an extra 0 in the denominator. So in general, as I was saying, you can have infinite rational numbers that may be inserted between any two given rational numbers. Keep this in mind and make a note of this somewhere so that you're very clear on how many rational numbers could be inserted between any two given rational numbers. Now that you've understood this, let's move to the second part of the problem. The second part of the chapter talks about how we could represent a given rational number on a number line. We also have understood so far that rational numbers are real numbers, which means these are numbers that can be represented on a number line. So let us take a simple example, as I just put that heading out for you there. Now let us take the basic definition. You know, rational numbers can be of two types. You can have rational numbers that are greater than 1. You could also have rational numbers, there you go, that are less than 1. Let's put this together and we'll figure out the first part. Let us do a case where we are trying to represent rational numbers. There you go, rational numbers that are less than 1, which basically means that we know rational numbers are of the form p by q. So p by q becomes less than 1, indicating that the numerator is less than the denominator. Now let us figure out how we could represent something like this. An example of such a case would be 4 by 7, and if you notice, 4 is less than 7. Let's take this. So what I now have is a number line, and I've put 0 on one side and 1 on the other side, because if it is less than 1, it should always lie between 0 and 1. Let us see how we can work this out. You see 7 in the denominator. I'm going to divide the space between 0 and 1 into 7 equal parts. If you count the parts now, you will see that there are 7 equal parts. 1, 2, 3, 4, 5, 6 and 7. Now what I'm going to do is I'm going to find the fourth part. That is the first part, second part, third part, and there you go. That's the fourth part, and that is the fraction that I am supposed to represent. That becomes 4 by 7 on a number line. Now similarly, if you notice, the second part becomes 2 by 7, 6 by 7 would be your sixth part, 7 by 7 would be your last part, which is also equal to 1. Let's take another case. Let's take an example 2, and the fraction that we are going to put in is 7 by 12. If you notice, this is also a case where 7 is less than 12, so this fraction must lie between 0 and 1. We're going to give you some time and we want you to try this. While you're working on this, please don't forget your initial concepts. This is a rational number that is less than 1. So your fraction should definitely lie between 0 and 1. I'll start working on it in just about now. So the first thing I'm going to start doing is draw a number line. I'm going to put 2 arrows on either side. I'm going to put a 0 on one end and 1 on the other. Now let us look at the fraction again. We notice that the denominator of the fraction is 12. So now I'm going to divide it into 12 equal parts. 3, 4, 5, 6, 7, 8, 9, 10, 11, and the 12th one will be on top of 1. So let's start numbering it now. We'll start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's your 12th part. Now let's start analyzing this. If you look at the first part, second part, third, fourth, fifth, sixth, 7th, we need to stop on the 7th part because 7 was our numerator. So the first part became 1 by 12, the 5th part became 5 by 12, the 7th part became 7 by 12. You try this one. And now that we have done about a couple of examples, I think this should be much more easier for you. Let's take in 3 by 8. Just give you about a minute to analyze this and put it on your book. I hope you've got it. We'll start working on it together now. I'm going to again start drawing my number line. There you go. Put 2 arrows on either side, put a 0 on the left, 1 on the right because my fraction is less than 1. If I look at my denominator, it is 8, so I'm going to start dividing it into 8 parts. 1, 2, 3, 4, 5, 6, 7, and 8. Now I'm going to find the third part and I'm just going to circle it. So let's start. This first part, second part, that's your third part, and that is going to be my fraction, which is, there you go, I'll just shade it, and that becomes 3 by 8. This must have been quite simple, isn't it? So with this, we are in a position to understand how to represent positive rational numbers. Let us see what happens when negative rational numbers come by. So the first case we're going to still look at is a case of a negative rational number which is still less than 1. So let's take the example of minus 3 by 7. If you notice, 3 by 7 is still a fraction that is less than 1. But since we're talking about a minus sign, this is going to lie between 0 and minus 1. Now the procedure is going to be the same. I'm going to divide this again into 7 equal parts. There you go. And then I'm going to start from the 0 end. There you go. And mark the third position. It's always essential that you count from the 0 end. So I've just made a list of it. That's your first part, that's your second part, and there you go. That becomes your third part, and that becomes minus 3 by 7. The most important thing you have to keep in mind is to count from the 0 end. Let's take another example. Let's take an example 2. Let us try and represent minus 4 by 9 on a number line. Again, if you notice, the fraction is less than 1. So you will have to represent this number between 0 and minus 1. This is a chance for you to try. We're going to review this in just about a bit. But before that, I'm just going to give you this note again. Always make sure that you're counting from the 0 end. Just going to put that up for you again. Always count from the 0 end. Let's draw a number line now. Put an arrow on either side. I'm going to put a 0 on the right side and a minus 1 on the left side. I notice that this has 9 as the denominator. So I'm going to divide this into 9 equal parts. There you go. And then circle the fourth part. So let us try and find the fourth part. There we go, we found the fourth part. Let us circle that fourth part, and that becomes minus 4 by 9. So this is how you could represent both positive and negative rational numbers that are less than 1. Now let us look at another case, one of your last examples for today under this category. Let us look at minus 3 by 17, and this is something you're going to try again. Again, make sure you're counting only from the 0 end. Alright, we'll start working with this now. I'm going to draw a number line, mark 0 at one end and a minus 1 at the other. Let us divide this into 17 equal parts. This is going to take a while. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and there you go, that's your 17th part. And I'm going to find my third part and circle it. There you go, that becomes minus 3 by 17. If you have any more doubts on this one, you could just leave a comment and I could look into it and I could review it and get back to you. But I hope this is clear largely from representing it on a number line. Now that we have understood how to represent numbers that are less than 1, let us try representing rational numbers that are greater than 1. There you go, representing rational numbers that are greater than 1 on a number line. So let's start with what an example of such a thing would look like. This is a case where the numerator is greater than my denominator. Let's take an example. Let's take an example of 5 by 3. You notice 5 is greater than 3. So this becomes a number that is greater than 1. The first thing that you'll have to do is convert this improper fraction to a mixed fraction. And I hope all of you know how to do this, but I'll just put it by the side so that you're aware of the process. So let us first divide 5 by 3. 3 times 1 is 3. You get a remainder of 2. So this becomes 1, then the remainder 2 divided by 3. Remember, the mixed fraction is 1, 2 by 3, which represents 5 by 3. Let us represent this number 1, 2 by 3 on a number line. I'm just going to put that number again there. That is 1, 2 by 3. I'm going to first draw a number line. Since I start with the number 1 in the fraction, the next number I'll have to immediately put is 2. There you go. That 1 that we've written there should go there, and the number after that, which is the next number, must go to the right. There you go. Let us look at the next step. You see 3, so we will divide this part into 3 equal parts. And then what we're going to do is look at the number that is above 3, which is 2, and find the second part, which is that one, circle it. Let's start circling this, yes, and we get 1, 2 by 3 as the answer. The only difference is that you convert this to a number line. I've just gone back to the previous slide so that you can just take a reference of this, and I'll give you maybe a few seconds just to memorize this. And now we go to the second page, and this is how it's going to look. Let's take another example. Let us try and represent 17 by 3. The first step I told you is to convert this into a mixed fraction. So I'm going to do 17 by 3. I'm going to get 2 as the remainder. So this can be written as 5, then the remainder 2 by 3. Now let's try to put this on a number line. Now this time the number line is going to start from 5 and the next number is going to be 6. This segment is now going to be divided into 3 equal parts that I just underlined, and then I'm going to pick up the second part, which is the 2 that we see. There you go. And then we're going to find the second slot. There it is, and that becomes 5 2 by 3. I'll give you a minute, just go through this. Let's try another one where you do it by yourself. You try this. Let's take 4 1 by maybe 7. All right, let's take 4 1 by 7, and I'll give you about a few minutes, maybe some time to just figure this out. I've made that a little easy for you. I've converted that into an improper fraction, which is 29 by 7, already into a mixed fraction, which is 4 1 by 7. That's for you to start representing. I hope you've completed it. We'll start now. Here's my number line. I'm first going to start with a 4 and then with a 5. I'm going to divide the region between them into 7 parts. There you go. And finally going to pick up the first part by circling it. So just make sure you put exact 7 parts, and now I circle the first part, and that becomes 4 1 by 7, or it is also 29 by 7. I hope this made sense. If it has, then let us try the next one with a negative sign. Let's try 7 1 by 3 with a negative sign. The process is similar. If you just know, the value will now lie between -7 and -8. So when I draw a number line like this, I'll have to put -7 on the right and -8 on the left, and I'm going to divide this into 3 equal parts. There you go. And then I'm going to choose the first part, and that becomes -7 1 by 3. And always remember to count from the side of 0, which is from the -7 end. Now that we've been able to represent -7 1 by 3 on a number line, this should give you a little bit of confidence on how to represent any form of number line, any form of number on a number line, I beg your pardon. And I think with this, we'll just summarize what we have done so far. We know rational numbers is something that we started off with today, and I said rational numbers by definition can also be terminating numbers, can also be non-terminating but recurring numbers. And when we talk about non-terminating, it is essential for us to understand that non-terminating numbers can also be recurring numbers, which are called repeating numbers, and these are numbers that also come under the family of rational numbers. Let's take an example of 2 by 5. If I convert 2 by 5 to a fraction, I get 0.4. I notice that my division stops at this point, so it becomes a terminating number, making 2 by 5 a rational number. Let us take another example, 1 by 3. If I try to divide 1 by 3, I notice I'm going to get a repeated pattern of 0.3333 all the way to infinity, which means you notice that there's a number that is repeating, which is 3, and it is completely non-terminating in nature, which is why you see those dots after the 3. Therefore, this number can just be represented as 0.3 bar, making this a non-terminating recurring number, which is also a rational number. Let us take an example now. Let us try and express the following numbers following rational numbers as decimals. This is very simple. And I've picked up a few questions from the textbook so that it's easy for you to work with. Okay, so 42 by 100. So the first thing I'm going to do is circle 100 because that's interesting. If you see, the decimal point is right after 2. So all I'm going to do is move 2 places to the left and you get 0.42 as the answer. The trick about dealing with division by any multiple of 10 is just moving decimals to the left. So for example, since we had 2 zeros in the denominator, we move 2 decimals to the left. If you also notice, 0.42 is a terminating number, which means you cannot divide it further. And since this is a terminating number, it is good for us to call it a rational number by the definition of rational number itself. Let's take another example. Let's take 327 divided by 500. And let us see how this can be worked out as well. Now, the best way to deal with this is do long division, which is what we shall do here. Let's quickly put up the space on the right so that we could start doing long division. So here we go. See, we put in 500 outside, 327 inside, and we start dividing it. This goes 6 times, 3000, leaves a remainder of 270. Put another 0, 5 times. You get 2500, subtract, you get 200, put another 0, you get 4 and a 2000. So if you notice, we were able to obtain a remainder 0 and get a quotient of 0.654, indicating that this 2 was a terminating number, making 327 by 500 a rational number. Now that we have understood what terminating numbers are going to look like, let us take another case where we get 2 by 3. Now let us try and understand how this is going to work. Let's start dividing this as usual. But before that, something that I want you to understand is, since this is already of the form P by Q, it is safe for us to call it a rational number. But we'll try and understand why it is a rational number. So I'm going to start dividing. I'm going to put 2 inside. There you go, 3 outside. Start with the decimal point. 6 times gives me 18. Put another 0 there. Another 18. Another 0. Another 18. If you notice, we are following a specific pattern here where the division continues to be leaving a remainder of 2 at all points in time, which means that this becomes a non-terminating number whose quotient is 0.6666 and so on. Since it is a non-terminating number, there is a good thing that we'll have to check here. We'll have to check if it is a recurring number or a non-recurring number. But something that you notice here is 0.6666 has a repeating pattern. There you go. It's a repeating pattern. And your repeating digit is 6, so you can put it in a concise way and just make it 0.6 and put a bar on top of it. The bar is put only on numbers that are repeating. Let's try minus 4 by 9. As usual, I'm just going to put the positive value first of minus 4 by 9, and then for the final answer I'm just going to attach a negative sign. So let's see how this is going to work. So I'm just going to erase that out. There you go. And now we'll start putting in the division together. We put a 4 inside and a 9 outside. Start with the decimal. You get 36, a 4, another 0, another 4, 36. So if you notice, you get a similar pattern here where you constantly keep getting 4 as your remainder. So the answer can be written as 0.444 with a couple of dots after that, indicating it is a non-terminating number again. And if you have to put this in a concised way, this is going to be 0.4 and a bar on top of 4 because 4 was the repeating number. I hope this was clear in terms of how a rational number can be a repeating number as well. Alright, now let us try and do a bit more. Now, a common question we get asked is, sir, is it essential for us to divide the number to find out if it is a terminating or a non-terminating number? The answer is no, and this is how we can determine if the given number is terminating or non-terminating. And let us try and understand how this is going to work. This is completely, as I said, without actual division. Alright, so we're going to take a couple of examples here, and this will help you determine that. So let's take the first example. The first example is 4 divided by 18. Now the first thing I'm going to do is try and cancel this out. That goes 2 times, this goes 9 times. So my answer is going to be 2 by 9 because it is expected to be in the co-prime format. And I'm going to take another number which is 1 by 16. So we have two numbers with us, 2 by 9 and 1 by 16, and we'll start working with both of them. The first thing that I'm going to do is circle the denominator on the first one and express it as a product of its primes. You know 9 is equal to 3 square, so 2 by 9 becomes 2 by 3 square. Similarly, 1 by 16 becomes 1 by 2 power 4. If you want to know how that works, I'm just going to quickly do the LCM method for you on the right side, so that you can just look at it and put the answer. You notice that there are 4 2's, so that becomes 2 power 4 as we have just indicated. Alright, now let us just look at the first number. The first number that we have is 3 square, and we notice 3 square is not of the form 2 power m into 5 power n, whereas 2 power 4 is definitely of the form 2 power m into 5 power n. Now you may ask me why there is no 5 power n there. All you have to do is assume that there's a 5 power 0 which is equal to 1. In general, what we are trying to tell you is, if your denominator is of the form 2 power m and 5 power n, which indicates your denominator consists of only the numbers 2 and 5, then it automatically becomes a terminating number. If it does not, for example, in the previous case, we had a 3 square, we noticed that there was no 2 and a 5 in the denominator, making it a non-terminating number. Now let us try and do this one. 8 by 15 can be written as 8 divided by 3 times 5. And again, if I look at the denominator, let's see if it has a 2 power m and a 5 power n in it. It has a 5. It also has a 2 in the form of 2 power 0. It also has a 5 power 1, but if you notice, it also has a little culprit there called the 3. Since you have an additional number apart from 2 and 5 in the denominator, this number becomes a non-terminating but a recurring number. There you go. It becomes a non-terminating but a recurring rational number, because a rational number can only be terminating, and if it is non-terminating, it must be a recurring number. Let's take another example. 1 by 50. Let's quickly do the prime factorization of 50 on the right side. There you go. 50. 2 times will give me 25. 5 times will give me 5. Another 5 will give me 1. So this becomes 1 by 2 power 1 into 5 square. Now if you look at the denominator, it consists of 2 power m in the form of 2 power 1. It also consists of 5 power n in terms of 5 power 2. It does not have any other number except 2 and 5. Therefore, 1 by 50 becomes a terminating rational number. I'm just going to put that out for you there. It becomes a terminating rational number. I hope this was clear to all of you. Now let us try and understand how to summarize everything we just told. So in general, I'm just going to try and tell you that if the denominator can be expressed in the form as 2 power m and 5 power n only, and there's no other number in between, then the given number becomes a terminating number. There you go. As you say, it is always terminating. Just remember the 2 power m and 5 power n. It could have either of the numbers or both the numbers, but nothing else. This is something that I want you to pause and make a note of, because this is exceptionally important from your examination point of view. It saves you a lot of time in the exam, and you don't really have to sit and divide each time. Alright, now let's go into the next part of it. It talks about expressing a terminating rational number in the form of p by q. This is very easy. Terminating numbers can easily be expressed in the form of p by q, and we'll take the first example. Let's take the first example of 0.15. Now we notice that 0.15 is a terminating number, and this is the first step we're going to do. We're going to take that number and divide that number by 1. Now what we're going to do is move 2 decimal places to the right, which will come as a part of step 2. So I'm going to start from that decimal and move 2 decimal places until I come to the end of the number, and if I move 2 decimal places, I'm going to put 2 zeros in the denominator. And my third step, I'm just going to simplify it for myself. So this becomes 15 by 100. Let us simplify that out a little. There you go, 3 times, 20 times. So your final answer is 0.5 can now be expressed as 3 power 20. I'm just going to put that in a box so that your presentation looks neat. I'll give you a minute. You could just go through this before we move to the next one. Let's try another one. Let us look at now hold on. I think what we could do is, I'll give you a decimal number instead. I think that would make things a little more easy for you. So let us try and express 0.675 in the form of p by q. So let's recollect some of the steps that we just did. The first step that we did, I'm just going to put that up there. Step 1 is where we divided the given number by 1, and then we counted the number of decimal places we could move to the right, and here we notice there are 3 places, so I'm going to put 3 zeros in the denominator. So this becomes 675 by 1000, and the next thing I'm going to do is cancel it off as a part of step 3 and put it in its standard form, which is 27 by 40. So your final answer is going to read 0.675 is equal to 27 by 40, and you're going to highlight your answer in a box. There you go. Remember, presentation is very, very important at a high school level, and always keep that in mind when you're working it out. There you go. All 3 steps are done, and this is how we're going to express terminating numbers in the form of p by q. Let's take another example. Let us take another simple one, 8.0025, and I want you to try this. Don't forget the steps that we've just illustrated. Always remember, step 1 is where you put that as divided by 1 and then move places to the right, and then try to simplify out your fraction. I'll just give you about another minute. Let's start. As I said, first write the number, divide that number by 1, and see how many places of decimal you could move. You notice that you could move 4 places of decimal, so that becomes 80025 by 1 followed by 4 zeros, each 0 for the number of decimal places you moved. And now you're going to simplify it, and you notice that on simplification you get 3201, divided by 400. Therefore, you notice that everything is in the form P by Q, and if you also notice that both of them have a HCF of 1 between them, indicating that both the numbers are co-prime. I hope this part of it was clear to you, to try and help you understand how we could represent terminating numbers in the form of P by Q. Now let us try and understand the second part of this. How do we convert recurring numbers into the P by Q format? It's a very valid question, because we just told you that they are rational numbers too, so they must also be in a position to be converted to P by Q format. Alright, so we'll take a very simple example, and this example will help us do it better. So here comes your first example. It's 0.3 bar. Now let us try and understand how this is going to work. The first step that you're going to do is you're going to write x is equal to 0.3 bar. Now you notice that there is one number under the bar, therefore you will have to multiply both sides by 10. If you see two numbers under the bar, you will multiply it by 100, and when you multiply it by 10, we're just going to show you how this multiplication is going to work. So you know 0.3 bar into 10 is what we're trying to do here. So this can be written as 0.333 etc. into 10. So I'm just going to move one decimal to the right, so this becomes 3.333 etc. into 10, making it 3.3 bar. So 0.3 bar into 10 now on your RHS right hand side becomes 3.3 bar. There you go. Now I'm going to call that as equation 1 and this is equation 2, and all I'm going to do is subtract both the equations. So I'm going to do 2 minus 1, and this is how you need to work with it. First you'll have to do 10x minus 1x. You always have to subtract the LHS and then put the RHS together. You're going to do 3.3 minus 0.3. Subtract them. You notice that everything after the decimal point is 3 bar, so that gets cancelled out, leaving behind 3. So you get 9x is equal to 3, and x becomes equal to 3 by 9, which is equal to 1 by 3. I hope that was clear. I'm just going to highlight my answer as usual. I'm just going to give you a minute to just look at this. If you want, you can pause the video and rework on this problem. Let's try another one. Let's take a case of 0.2 bar. As usual, my first step is I'm going to put x equal to 0.2 bar, and I notice that there's one number under the decimal point under the bar, therefore I shall multiply both sides by 10. So I get 10x is equal to 0.2 bar into 10, which is going to show that multiplication again for you. On the right hand side of the screen, you see 0.2 bar into 10 becomes 0.222 into 10, which is 2.2 bar, as we just did in the previous problem. So now what I get is I get 10x equal to 2.2 bar. As usual, I'm going to mark my first equation and my second equation, and I'm going to subtract both. So 2 minus 1 would give me 10x minus x, which is equal to 2.2 minus 0.2. I'm just going to put one below the other so that it helps you understand it. 2.2 minus 0.2. So when I subtract it, I notice that all my 2 bar beyond my decimal point gets cancelled off. My LHS becomes 9x, and what I'm left on the RHS is 2.0. This implies x is equal to 2 by 9, and I'm just going to highlight that answer, and that is going to be your final answer. I'll just help you pause and work on this. You can always verify your answer by using a calculator. So what all you have to do is divide 2 and 9 on the calculator and check if you get 0.2222 as your answer. That is the most fascinating thing about these problems. You always know if you're right or wrong. Alright, I'll give you a case where you try something now. Let's try 0.5 bar, and you're on your own. I'll do it in a bit, but I want you to try it. If you want, you can go back to the previous problem and see if you can get certain clues, and pause the video at this time. Alright, I hope you got it. I'm going to start working on it now. The first thing I'm going to do is I'm going to make x equal to 0.5 bar. I notice there's one number under the bar, so I'm going to multiply both sides by 10. So I'm going to get 10x is equal to 0.5 bar into 10. You as usual know 0.5 bar into 10 is 0.555 etc. into 10, making it 5.5 bar. There you go. I'm just moving one decimal place. I'm just reiterating this so that your multiplication becomes easy. So this becomes 5.5 bar. Then as usual, I have my first equation. I also have my second equation. I'm going to do 2 minus 1, and that will give me 10x minus 9x. Sorry, 10x minus x is equal to 5.5 bar minus 0.5 bar. My left hand side is going to be 9x and my right hand side is going to be 5. So x is now going to be equal to 5 by 9. I'm just going to highlight that. There you go. I'll give you another problem that you could try now based on everything that we have given. Why don't you try let's take maybe 0.6 bar. Yeah, there you go. I'm just going to erase that and put that up for you again. I want you to do 0.6 bar. You can pause the video at this stage, finish it, and then continue with it. Alright, I'm going to start working on it now. X is equal to 0.6 bar. So then again it's going to be 10x is equal to 6.6 bar. I'm going to subtract both. That's equation 1 for you. That's equation 2. I'm going to subtract both. So I'm going to get 2 minus 1. 10x minus x is equal to 6.6 bar minus 0.6 bar. So that is going to give me 6. I have 9x on my left hand side. So x becomes 6 by 9, which has to be further simplified to give me 2 by 3. Always remember, your numerator and denominator must be co-prime when it comes to one another. There you go. Now let me take another case where there are two numbers under the bar. So I'm going to take this example of 0.32 and both 3 and 2 are under the bar. Now here we notice that there are two numbers under the bar. Therefore, it is essential for us to multiply both sides by 100. So it's going to be 100x is equal to 0.32 into 100. I'm going to show that on the right hand side. This is going to be 0.32 bar into 100. So this becomes two places of decimal again. 0.32 can be written as 0.3232 and so on into 100. I'm just going to move two decimal places to the right and I'm going to get 32.3232 etc., making it 32.32 bar. So now I have 100x is equal to 32.32 bar. I'm going to call that equation 1. Second one is equation 2, and I'm going to follow the usual process of subtracting both the equations. So 2 minus 1 would give me 100x minus 1x is equal to 32.32 bar minus 0.32 bar. When I subtract, I notice that everything to the right of my decimal gets cancelled off. So I get 99x is equal to 32. So x becomes equal to 32 by 99. And please verify your answers in a calculator if you think you're probably going wrong somewhere. But always remember that you cannot use a calculator in the exam. Let's take another one, and I want you to try this. This is 0.61 bar. And while you're trying to do this, keep in mind the steps that we've just focused on. You notice that there are two numbers under the bar, 6 and 1. So you'll have to multiply both sides by 100. And as you're doing this, I'll give you a little time. I hope you got it. I'm going to start working on it now. So I'm first going to say x is equal to 0.61 bar, and then I'm going to multiply both sides by 100. So I'm going to get 100x is equal to 100 into 0.61 bar. I'm just going to quickly show that for you. So that's going to be 0.61 bar into 100, which is going to be 0.6161 and so on into 100, which is going to give me 61.61 bar. So when I put that together, I'm going to get 100x equal to 61.61 bar, and I'm going to call that one equation. So that's equation 1 for me, and that's equation 2 for me. Then I'm going to subtract 1 and 2. I hope you've done exactly that. We're going to get 100x minus x is equal to 61.61 minus 0.61 bar. The 0.61 bar post the decimal point gets cancelled, and I'm left with 61. I get 99x is equal to 61, so x becomes equal to 61 by 99, and that's your final answer. Please highlight it, because that is how you're going to present it. I hope this is clear. We'll start with an example. This is going to be example 3, and this is going to be an interesting example. Please make a note of it. It is 0.1, 2, 3, and all three numbers are under the bar, and I want you to try this based on what we've just done. Please mind the number of digits that are under the bar, and then work on what you're supposed to. I hope you were able to do something about it. I'm going to start now. I'm first going to say x is equal to 0.123 bar, and then you may have done it well. I'm not going to multiply it by 100. If I do that by 100, then I'm not going to get the right answer. So that is going to be incorrect. So I cannot multiply it by 100. Since there are three numbers under the bar, I will have to multiply it by 1000. So that is going to be 0.123 bar into 1000. What do you think 0.123 bar into 1000 is? I'm just going to show that on the right. It is going to be 0.123 into 1000, which is going to be 123.123 bar. I hope that's exactly what you got as well. So I'm going to put that value down here. So I'm going to get 1000x is equal to 123.123 bar. That's my second equation. That's my first equation. This is my second equation. And then, as usual, I'm going to do 2 minus 1, and let's see what we get. So this gives us 1000x minus x is equal to 123.123 bar minus 0.123 bar. As usual, my 0.123 post my decimal gets cancelled, so I'm left with 123, which is equal to 999x. So my answer is going to be x equal to 123 divided by 999. And mind you, these are two numbers that can be divisible by 3. So that's exactly what I'm going to do. So I'm going to cancel both by 3, and I'm going to get 41 divided by 333. And that is going to be my final answer. There you go, 41 by 333, and I'm going to go put that in a box. Let's take another problem now. This is another interesting problem. This is the next level. So I have x equal to 0.12, and please mind it that only 2 is under the bar. I'm just going to put that there. The bar is only on 2. I'm just going to quickly show you how this is going to work. When I read this number, I'm going to read it like this. This is going to be 0.12222, and since the bar is on 2, it is the digit 2 that keeps repeating. Alright, so let's figure out how we're going to do it. Since we have just one number under the bar, I'm still going to multiply it by 10. I'm going to push one decimal to the right, and I'm going to get 1.2222, which is nothing but 1.2 bar. That's 10x for me. As usual, I'm going to write my first equation and my second equation, and then I'm going to subtract both the equations. So 2 minus 1 will give me, there you go, I have a 10x minus x, which is going to give me a 9x, and that is going to give me 1.2 bar minus 0.12 bar. Now this is the tricky part of it. You'll have to be a little careful here. So I'm just going to modify my 1.2 bar as 1.2222, just going to expand that out a little, and then I'm going to write the one below as 1.2222, sorry, 0.12222. Do you notice that there's a 222, what I've just highlighted, to be the repeating number that completely gets cancelled out for me? So I'm going to be left with 1.1, and that is going to be equal to 9x. So I'm going to say x would be equal to 1.1 by 9, and when I simplify that out further, I'm going to get the answer as 11 by 90. This is the only little change that you'll have to make, but you'll figure out as we do more problems on this. I'm just going to give you about a few seconds to go through this page before we go into the next one. Alright, let's begin with another one. Let's take x equal to 4.18, and as usual I'm going to put the bar only on a single digit. So as usual, since there's one number under the bar, I'm going to multiply both sides by 10, and I'm going to get 41.8 bar. I've skipped that step because I would like to believe that you've already learnt it. I'm going to call that equation 1, and this is equation 2, and I'm going to do 2 minus 1. Please be a little careful with this step. This is going to be 10x minus x. It's going to be 41.8 bar minus 4.18 bar. Mind the place value system. Just open out each one of it. Just expand this out for me. 9x is going to be equal to, I'm just going to show that on the right. So that is going to be 41.8888 and so on, minus 4.188 and so on. So when I subtract it, I notice that the 8 has a repeating pattern, so that completely gets cancelled out for me. So I'm going to get 37.7. So I'm going to just put that value there. So 9x is now equal to 37.7, and x becomes equal to 37.7 divided by 9. So if I put that together, I get 377 divided by 90, and I'm just going to highlight that out a little. I hope that made sense to all of you. Just giving you about a few seconds. Let's try another one, and this is something I want you to try. Let's put x equal to 2.18, and I'm going to put the bar only on 8, and I want you to try this. You can pause, you can go back to the previous few minutes and see what we did in the previous problem, and then you can try it by yourself, and then I'm going to do it for you. I hope you were able to do it. Let's begin. Since I have one number under the root, I'm going to start directly by putting 10x. I'm going to say 10x is equal to, there you go, 2.18 where the bar is only on 8 times 10, and this is going to give me 21.8 bar. I hope you got that. And now I'm going to mark my equation 1 and 2 again, and I'm going to show that little calculation on the right when I do the 2 minus 1. So that's going to be 10x minus x, which is going to give me 9x. So first my 10x is going to be 21.88 bar, then that's going to be subtracted by x, which is going to give me 2.18 bar. Observe where the repeating 8s start from. I'm just going to highlight that out for you. 9x equal to, if you notice, that is the highlighted part which needs to go. So we'll end up getting 19.7. So x becomes equal to 19.7 divided by 9. I'm just going to move one decimal place to the right, and I'm going to get 197 by 90, and I'm going to highlight my answer. I'm just going to pause for a few seconds. I want you to try this one. I'm sure you're a little more confident right now with whatever has happened. So I would just want you to sit and try this. This is going to be x equal to 0.123, and the bar is only on 3. You can pause the video at any point in time if you feel it's necessary. So I shall begin doing this right now. Since there's one number under the bar, I'm going to begin by writing 10x equal to 10 into 0.123 bar, which is going to be 1.23, and the bar continues to be on that single digit that we've listed. That's equation 1 for me, that's equation 2 for me, and I'm going to subtract both. When we subtract both, we get 10x is equal to 1.2333 minus x, which is equal to 0.1233, and so on. Observe the repeating pattern and cancel it off from there. Let's subtract this now. I get 9x. That's your repeating pattern. Cancel that off. So on the RHS I get 1.11, and on the LHS I get 9. So x becomes equal to 1.11 by 9, which is going to give me 111 by 900, which can be further simplified. You can divide both the numerator and denominator by 3. So I'm going to get 300, and then I'm going to get 37. I'm going to highlight that answer, and that is going to be our final answer. So from this, it's quite clear that you know how many digits you need to work with and multiply it by what factor of 10. We'll try another one, and this is again on you. You try this one. This is going to be 0.00352, and we're going to put the bar only on 5 and 2. I hope you were able to figure it out. Let's quickly start with it. First, I'm going to say x equal to 0.00352. I put that under the bar, and I see 2 digits under the bar, so I'm going to multiply it by 100. I'm going to move 2 decimal places. I'm going to get 0.352, and 52 comes under the bar, and now I'm going to subtract it as usual and find the repeating decimal places and cancel them off. So that's 2 minus 1 again. You can just follow it as I put it up here. So that's going to be 0.352 minus, just expanded that out for you, minus 0.00352 cancel that off. I'm going to get a 0.349, which is going to be 99x, and then I'm going to put that together and get my answer. There you go. I'm just going to put that in a box, and that is going to be my final answer. Let's try another one. X equal to 15.712, and bar is on 1 and 2. This is something I want you to try. Go back for the steps if necessary, but I think this is something that I'm sure you would have done. So let's begin. There are 2 digits under the bar, so I'm going to begin with 100x. Let's directly see how we could work on this. This is going to be 1571.212, and 12 is as usual under the bar, so that comes in up there. And then I'm going to directly subtract, getting 99x equal to 1571. Just going to put out that there, 1571.212 bar minus 15.712 bar. This is easy. This is just going to get cancelled off because that's your repeating pattern. Just find the difference. So I'm quickly going to do the borrowing and subtraction here. So that is going to give me a 5. Then this side will give me a 1555.5. So I have 99x equal to that. So x becomes equal to 155.5 divided by 99. As usual, I'm going to move out 1 decimal place. I'm going to put a 0. And then I'm going to put that out there and simplify it so that it makes sense. You notice that we can cancel both numerator and denominator by 3. So we're going to get 5185 by 330. And I'm going to highlight that out for you so that you exactly know how to present it out well. Alright, so this covers a large part of your chapter, and we've already covered rational numbers. So we're just going to summarize what we have covered so far before we end this part of the module. We've understood what rational numbers are, and under rational numbers, the first thing we spoke about was inserting rational numbers between any 2 rational numbers. At any point in time, if you have a doubt, you can always go back and go through it once more. The second part of it was representing rational numbers, and you guessed it right, it was representing rational numbers on a number line. Third one was expressing them in the form of P by Q, which is their standard form. So that was expressing them in P by Q form. And we did this for both terminating as well as non-terminating recurring numbers. And the last one we spoke about, that's D, is going to be rational numbers, can always be of two types. The first type of rational numbers are terminating rational numbers whose division terminates after a point, and then the other one is non-terminating numbers, and if they are non-terminating, it's important that we always consider them to be recurring. Alright, with this we have completed the first part of the module. I hope this was useful to all of you. While we work on the second module, please keep updated with our channel and subscribe for the latest updates. Thank you very much and have a great day.